All right, back again. This is the first theory video, mostly theory anyway, on rotation of axes, which is chapter 11, section 5. So I'm going to go through this and I will follow up with a few worked out examples. Um, I'm probably not going to go into this as deeply as it is in the textbook, but this should still work out well. Okay, so conic sections can be represented both geometrically and algebraically. And don't forget, from a geometric point of view, if you go back to the first video or the first set of notes on conic sections, we saw two cones that were joined um, at a vertex, and we passed planes through them, and that's how we generated the conic sections. We would get a circle, we'd get ellipse, parabola, hyperbola, and if the intersecting plane went through the nape, meaning where the common point where the two cones met, then you would get something called a degenerate conic, which would be a point, a pair of lines, a single line, things of that type. Okay. This is all on Blackboard. There is a file called Rotation of Axes Notes, and I'm going to try and stick with that and talk through it a little bit. Okay? All right, the equations of the conic sections we've considered so far, and that means circle, parabola, ellipse, and hyperbola. Those are called the degenerate conics. Those generally have the formula ax squared plus cy squared plus dx plus ey plus f equals 0, where a and c are not both 0. Now, one of the things that we will be practicing is we can identify a conic without completing the square. Let me see if I can make this a little better. Okay. And this occurs when A and C are not both 0. And I've sort of talked through this a couple of times, so it shouldn't be that alien to us. If A times C equals 0, and they're not both 0, it means one of them is, in which case we get one of the variables squared and the other is not squared. That will be a parabola. You know, like y squared equals something or x squared equals something. If the product of A times C is greater than 0, means the signs are the same, we get an ellipse. We get a circle if A and C are equal, but generally we get an ellipse. If A times C is less than 0, meaning the coefficient of the x squared and the coefficient of y squared, if their product is less than 0, meaning they have different signs, we generally get a hyperbola. Okay, now the catch is, this stuff is true provided the conic is not a degenerate conic, meaning it's not point, pair of lines, or single line. Okay, so a couple of examples, and you can work through these for yourself, and most of them are pretty easy to see. Like I would look at number 1 and I would say, okay, the signs are the same in front of the squared terms, so probably an ellipse, and definitely now because A and C are different, so it's an ellipse. And if you put this in standard form, you will see, yes, it is an ellipse. Okay? You couldn't really tell that 100% here. You have to watch out sometimes. So, you take a look at a few of these. And let's look at number 2. The x squared and y squared terms are both present. You have a negative 1 in front of the x squared, positive 4 in front of the y squared. Their product is negative, probably going to be a hyperbola. And I use the term probably because if it's a degenerate conic, of course, that's not true. But at any rate, so looking at number 2, I took the time right here. So I did some work and I put it in standard form. You can see, yes, it's a hyperbola. Okay, so you should look at the rest of these. I am going to point out number 6. We have a 1y squared and a negative 1x squared. And most of the times this was going to be a hyperbola. However, there's a special situation which is going on here, and the only way to really check that is to put it in standard form. And that's why we have all these cautions here. So if you take number 6, you do the testing. A times c is negative. Clearly, so you think it's a hyperbola. But if you go ahead, it turns out that you get a 0 here. And what that means is if you push this term over to the other side, take a square root, you get a plus or minus, and then add 2, what you get actually is a pair of lines. And that will occur in a situation where the plane that cuts the double cone is running right along one of the edges of the cone. So you can picture that if you go back and take a look at some of the illustrations in the textbook. But sometimes this can happen. Also notice in number 5, it looks like a perfectly well-behaved standard form, well, not quite standard form, but it looks like this form here, right? Ax squared plus cy squared, so forth and so on. Looks perfectly well-behaved. You have the same signs in front of the x squared and y squared. You have the same numbers of 1. You suspect it's a circle. And it actually is a circle, but there's a catch. Turns out that when you do the computation, unless I did this incorrectly, that there's a 0 here, which means it's a circle centered at -3, 2 with a radius of 0, and we call that a point. So you do have to be a little bit careful in working problems of this type. So when I do give a problem set, I'll put one up maybe later today or tomorrow, probably due in 5 or 6 days. These are some of the things you have to watch out for. Okay, now notice we left out the letter B in the alphabet. And the reason why we did that in this form is because the general second degree equation includes an xy term as well. It has this kind of form. Now when B is non-zero, what typically happens, and of course you have a degenerate type of situation can occur as well, but generally if B is not a 0, so this term is present, that represents a rotation. And a rotation of, and we'll talk about this in a little while, and a rotation of a conic section generally through an angle theta. And I'm going to prove this later on, but this is the relationship that we're going to use. Tangent of the double angle is B over A minus C. All right, I'm going to stick to ones that are pretty reasonable, I think. But at any rate, so let's take a look at what this is saying. Fixed point P can have several ordered pair representations depending on the coordinate system. And here's an example. I'm actually looking at a picture here. Okay, see if I can, okay, make that a little better. Okay, so we have point P here. And if we're looking at the XY coordinate system with the axes are in black, we would say P has coordinates x comma y. We're going out x and up y. Okay. However, if we take our coordinate system and we rotate it, here's a picture of what that might look like by an angle theta, then we can see that in the x prime y prime coordinate system, the y is a lot shorter. I mean, y prime is a lot shorter than the original y. X prime looks like it's a little bit longer. But the point is, if you change coordinate systems and you go with the red axes, x prime, y prime, you get a different representation for point P. Okay, so what this is talking about up here is related to the diagram here. All right, so let's just read it. Visualize P, x comma y, in the xy plane, and P, x prime y prime, in the x prime y prime plane, as shown below, where r represents the distance from origin O to point P. Now that hasn't changed, but what has changed would be the coordinate system. So here's what we're doing. We have two angles here. Angle theta represents the rotation of the coordinate system, and angle alpha represents the angle between the new x prime axis and OP. Okay, and our goal here is to represent or to express x and y in terms of x prime, y prime, and theta. Okay, so let's take a look at this. Now, from our second diagram, looking at diagram B, x prime, well here, if you look at this triangle here, you have x prime, you have a perpendicular length y prime, then you have r. And it turns out that cosine of alpha is x prime over r, therefore r is, or x prime is r cosine alpha. And similarly, sine of alpha, y prime over r, and y prime is r sine of alpha. Now we've done this type of thing many times in the past. Okay, similarly, if we're looking in an xy coordinates system, this giant angle here is theta plus alpha, and you get these relationships. Okay, so what we're going to do is we're going to work with these, and all that really you need here is this boxed result, but I'm going to show you where it comes from. We start with x equals r cosine theta plus alpha, and here we apply the identity which we've done earlier, previous chapter, for cosine, the sum of two angles. So you get cosine theta, cosine alpha, minus sine theta, sine alpha, and for the sine of theta plus alpha, we get sine theta cos alpha plus cos theta sine alpha. And we go ahead, we're going to multiply this out, and we're going to regroup. So the r is multiplying this term and this term, and I'm going to associate the r with the cosine alpha. And if you take a look at that, look at what you got here. Holy cow. So this is nothing other than x prime. And over here, we push the r through, you get r sine alpha, and look at that, r sine alpha is y prime. So this gives us x equals x prime cos theta minus y prime sine theta. And if we did the same type, we follow the same type of reasoning here, we get y equals x prime sine theta, y prime cos theta. And these are called the rotation formulas, and we're going to use them. Okay, the derivation simply is there so you have an understanding maybe of where it came from, but we're going to use these. And this is not a memorization item, this is something you simply use. Okay, so next step, example number 1. Example number 1 says express the rectangular hyperbola. You learned this in high school, so we're looking at the blue here. xy equals 1 in terms of a new x prime y prime coordinate system by rotating the axis through a rotation of 45. Now, this is not the kind of hyperbola that we're used to. We're used to the hyperbola crossing either the x-axis, that was called type 1, or the hyperbola branches crossing the y-axis, that was called type 2. In this type of hyperbola, xy equals 1, neither of that happens. So what we want to do, and the whole purpose of this, is to do a rotation through an appropriate angle. It turns out that's 45, and I'll explain why. To do a rotation through an appropriate angle to transform the hyperbola into one that we're more comfortable in dealing with in terms of dealing with its standard form. Okay, so we're not moving the hyperbola, that's fixed. What we're doing is we're rotating the axes to get a nicer looking equation, okay, one that we're more familiar with. So that's the plan. Now in this case, we're simply told to use 45 degrees. Now, of course, how would you know that? Well, if you go back here, and we didn't prove this, I'm going to prove this in a little while, tangent of the double angle is b over a minus c, where theta is the angle of rotation of the axes. And a, b, and c are the coefficients rather, in our second degree general form. Okay, so let's go back here. And in this case, ax squared plus 1xy plus cy squared, yada, yada, yada. A and c are both 0. And the coefficient of this term would be the b, that's the 1. So using that, I'm plugging into tangent of 2 theta is this formula, which I'm going to prove in a little while. B is a 1, a and c are both 0. And 1 over 0, of course, is undefined. And we're supposed to know from our basic graph of the tangent curve that tangent is undefined at odd multiples of pi over 2, odd multiples of 90. So 90 and 270 and so forth, negative 90, negative 270. But the world that we're in, we're looking at 90. So therefore 2 theta is 90, theta is 45. So we did not do that here. I just told you use 45, okay? But that's why 45 degrees would be the angle of choice. Okay, so here we go. Let's apply our formulas. And the formulas that we're going to use are these right here. Okay, these are called our rotation formulas. Okay, so we get x equals x prime cos theta minus y prime sine theta. And what we're going to do is we put in place of theta, we put in the 45. And you've got the other one over here, y equals x prime sine theta plus y prime cos theta. And that appears here. And all we did is we put in the 45. So, okay, cosine and sine of 45 are add 2 over 2 in each case. So we put it in. X prime times rad 2 over 2 minus y prime times rad 2 over 2. We're going to factor out the rad 2 over 2. And we get x equals rad 2 over 2 times x prime minus y prime. Okay? And we do the same thing for y. You get x prime rad 2 over 2 plus y prime rad 2 over 2. Factor out the rad 2 over 2. You get this expression, and that's your y. And going back here, our formula is x, y equals 1. So I'm going to multiply, whoops. What happened? Okay, so I'm going to multiply then these two, because the expression says x, y equals 1. So here's the x, here's the y. You multiply them out. Rad 2 over 2 times rad 2 over 2 is rad 4 over 4, which is 1/2. And then I FOIL this out, and I get x prime squared minus y prime squared, and I simply divide by 2, and this would be the hyperbola, its standard form, okay, which is in the x prime, y prime coordinates. Right, and we can see that this is more, we're more used to using it in this form. Okay, so the general idea is, from the above example, a rotation of axes through an appropriate angle theta can transform a second degree equation with an xy term into an equation x prime y prime coordinates in which no x prime y prime term appears. So that's the idea. So what we're going to do is we're going to practice picking an angle, figuring out the angle, of course, and then going through this process, and we're going to get an equation which we can deal with in a much more sensible way, because we've already learned about finding foci and vertices and latus rectum and type and asymptotes. So for this type of curve anyway, so that's why this is useful. Okay, so let's talk about finding angle theta, and then we will, if we have time, we'll do an example. If necessary, we'll come back and do a second one in a second video. All right, finding angle theta. So here we go. So what the plan is, I'm going to derive the formula we used here. And again, the derivation is because that's what mathematicians do. They like to know why things work. But memorization, we're not going to memorize this. So to find angle theta, we begin with this equation. This is our general second degree. We're assuming b is not 0. And we're going to rotate through an angle theta using the rotation formulas. And here they are. Okay, so every place I had an x, I'm going to put this monster. Every place I had a y, I'm going to put this monster. And that's where this comes from right here. Okay, so that's where that comes from. It's a times x squared. Here's what I'm using for x. bxy, so here's the x, here's the y, so forth and so on. And then guess what? We're going to square these things. We're going to collect like terms. It's a real pain in the gluteus maximus. We're going to do it once just to show you that these formulas have reasons for why they are what they are. Okay, so I'm just going to go through this real quick. we're going to we squared this out. This term squared plus that term squared minus 2 times the product. And looks like I lost a sign here. This, if I got this right, okay, this should be a negative. I'm going to have to change that. Okay. All right. So at any rate, I'm going to go through and check all these signs, and I'll update this for you to make sure. But I'm believing this should be a negative. Oh, wait a second. No. I take that back, because what I did here is I squared this, and then I collected all the x squared terms. Okay, so any term that had an x prime squared in it, and I get that from a couple of different places. I get it from here, of course, and I'm also going to get it from here. Okay, so that's why that's a plus. And then where else am I going to get an x squared term? I'm also going to get it from here, right? Because this is squared. Okay, so this is not incorrect. This is correct. Okay, so what I did here is I expanded everything, which I did not show, and I collected like terms. So in other words, I'm going to get an x prime squared term from this part squaring, from the multiplication here, and from the squaring here. And those collected, I get this. All right, so here's what happened. I did the same thing for the x prime, y prime terms, for the y prime squared, so forth and so on. So since we want the coefficient of x prime, y prime to be 0, this guy right here, right, from here to here, this is not doing well. From here to here, this has to be 0. So I pull that term out, and I'm setting the coefficient here equal to 0, and I'm going to solve. And before I do that, I'm going to make a couple of changes here. Notice cos squared minus sine squared, the same angle as cosine of the double angle. We learned that before. And I've got a 2 here. 2 times sine theta cosine theta is sine the double angle. So that very nicely comes here. I move this term over, divide by cos of the double angle, and this is what I get. I get this quotient is b over a minus c, and sine of an angle over cosine of the same angle is tangent. Okay, so that gives us our tangent of the double angle formula. Okay, and that's what we're going to use to find theta. Now, in the next video, I'm going to do an example in great detail. I'm going to give you a chance to work through it first and take a look at it. It's actually easier than it appears. Okay, so I'm going to want you to take a look at that, and I will come up, well, maybe we have time. Yeah, let me do it now. Example number 2. By rotation of axis for an angle theta, transform this equation to its simplest form. All right, simplest form for us is going to be one of the forms we've already investigated, which we call standard forms. And you're going to notice that a rotation is necessary because I do have an xy term here and it is non-zero. So here's what I did. I broke this down for you in 3 steps. The book doesn't quite do it like this, but I think this is a little easier. Step 1, find angle theta. Step 2, apply the rotation formulas. And step 3, substitute x and y into the given equation. And when the smoke clears, if you do this right, this is not an easy task, you're going to get something which you recognize. Okay, so here we go. First of all, let's find angle theta. Well, a is a 1, it's coefficient of x squared. C is a 2. And radical 3 is the b. So I put those into my formula. Tangent of the double angle is b over a minus c. And I get negative radical 3. And then you got to think a little bit. You got to go back to techniques that we've used earlier in the course. Where is tangent negative? Now, for the time being, don't worry about the double angle. All right, the book deals with that. I'm not going to deal with that right now. Just take a look at this, and the double angle is negative, so tangent is negative in quadrants 2 and 4. The context, we're in quadrant 2. Okay. So therefore, I'm in quadrant 2. Now, the definition of tangent is opposite over adjacent. So I don't have this as a fraction, but you can visualize it's a radical 3 over 1, and one of them is negative. So opposite over adjacent, and the negative goes here with the 1. Pythagorean theorem, that's a 2. And then this is a special right triangle you're supposed to recognize. The reference angle, of course, is 60. Okay, this would be 30 up here. This is a 60. So the full angle, the double angle, is 120, right? Because this is a 180, and less 60 is 120, so theta would be 60 degrees. So what that means is, if we rotate the axis 60 degrees, we're going to get, whatever this is, turns out to be an ellipse in standard form. So I made a nice diagram for you here. All right, the ellipse, of course, is in green. Okay, and in case you're curious how I graph this, I used the program called Mathematica, and I used a contour plot, so you can put it in exactly like this, and even though it's not a function, right, fails the vertical line test, Mathematica will graph it for you. Okay, not easy to use, but at any rate, so you got your x and y coordinates. Okay, those axes are in black. There's your equation, and x prime, y prime, those axes are rotated. This angle here would be 60 degrees. That's what we're finding out. And according to that, if you take a look at the red axes and the hyperbola, rather the ellipse, it's a type 2. Okay, you may have to tilt your head to the left a little bit and look at it, but definitely it's a type 2. And the vertices, this is your 2A, this length here, this is your 2B, and it makes life a lot easier for you. Okay, so at any rate, let's apply the rotation formulas. That's step 2. Once you know you've got 60-degree rotation, here are your formulas, which you're not memorizing. Please don't do that. Your head will explode, okay? And you're going to plug in 60 degrees for theta, and you're going to work this out. Now, you're supposed to know. We've done this like a million times. Cosine 60 is a half. Sine of 60 is right 3 over 2. Do the same thing here. Sine of 60 right 3 over 2. Cosine 60 is a half. I work this out, okay? And just for the computation later on, I notice I have a 2 on each of the bottoms, the denominators. I factor out the 2. Did the same thing here. So these are the x and the y, okay? And then unfortunately, what I've got to do, and this is not that easy. It's a pain in the neck. I have to go back to my original equation, and in place of x, I'm putting this, and in place of y, I'm putting this expression. I got to do all the computations, and when the smoke clears, I get an equation I'm going to recognize in standard form. All right, so let's go through it. This says x squared, so I can square this. Half squared is a quarter. This binomial has to be squared. We'll do that the next step. Then I get radical 3, x times y. So here's your x, and there's your y. And the next term is 2y squared. So I got my 2 on the outside. This has to be squared. I already squared the half, got a quarter. Yet to square this. Minus 10 equals 0. So I do some work. All right, you should be able to square a binomial pretty easily. First, I notice I've got a quarter here, and over here, the product, half times half is a quarter. I got a quarter here, so I multiply everything by 4, which is going to kill the fractions, and I'm left with a radical 3 in front here, and I'm left with a 2 in front there, and now I'm just going to do the algebra. Okay, so this guy squared, and this guy squared, right? And the middle term, of course, is twice the product. That's minus 2 radical 3 x prime y prime. Do the same thing here. FOIL it out. This times this is radical 3 x prime squared. I get x prime y prime, and a minus 3 x prime y prime, which is minus 2 x prime y prime, so forth and so on. I go through the process, and of course I gotta multiply it out. I know, it ain't easy. So at any rate, don't do anything here, but this becomes 3 x prime squared. Here's a 6x prime squared. So 3 and 6 is 9, plus 1 more. That's how I got my 10x prime squared. Let's do the y prime squared. So I got 3 over here. Look at that. Negative 3y prime squared and 2y prime squared. Okay, so I've got 3y prime squared here. I get a negative 3y prime squared there. They cancel. plus 2y prime squared, I get that. Move over to 40 equals 40. I'll leave it to you, but you can check out that the coefficients of the x prime, y prime terms cancel out, they get 0. Let's do it anyway. So I got 2 radical 3, and over here, minus 2 radical 3, x prime, y prime, they're going to go. Oh, sorry, made a mistake. Negative 2 radical 3, and another negative 2 radical 3, that's negative 4 radical 3, and over here, I got positive 4 radical 3, they will cancel. So here's my fixed up equation. Notice if you do this properly, the b term, the coefficient of the xy, is going to become 0. So if you're really brave, you can sort of forget that and not even think about it, but I'm not that brave. I think you should think about it. In standard form, you want a 1 here, divide by 40, and you can see now this is an ellipse, okay? X prime, y prime axes, so that would be the equation of the ellipse with the red x prime, y prime axes, and that should be easy now for you to realize what your latus rectum and equations of asymptotes are, but they will be in x prime, y prime coordinates, understand that, okay? So let me leave this for the time being, and what I will do is, I guess that's good enough, because I'm probably not going to give you anything to work out where the rotation angle is either going to be a 30, a 60, or a 45. Right? I'm going to be reasonable with this. The book goes into some crazy things. I don't think for us it's really necessary. Okay? If I were doing a face-to-face class, I would say, okay, I'll do it step by step with you, and I'll expect maybe a little more. But since you're sitting down and doing this basically on your own and with these videos, I'm probably going to give you a rotation of 30, 60, or 45. Okay? All right, so be that as it may, take a look at this, and I'll see you in the future. Okay, and I will post up a problem in this topic in the near future. Thank you.